Another one is the scale factor, or the size of the universe. I love this from Redshift. I want all the data. This is actually taken from a really nice blog, actually, that I really like. She doesn't write anymore, but yeah, it's a great image that she had done. What was it called? Hyperbole and a half, I think was the original name. Anyway, I wanted to show you this. This is the size of the universe. We call it scale factor. But the size of the universe, the problem is we don't really know what units to put here. It's kind of funny because we don't really know what values to put here. We're like, I don't know, because it's in 4 dimensions, right? I mean, it's space-time, so how do you draw that? We don't. We just, size of the universe, 0, and then bigger. We don't even know what numbers to put in here. Time even is awesome. Like, well, there must have been a 0. There must be some time where we are now, and then later. So that's a little bit crazy, but you still can look at these sort of things and try to guess some things about the universe. So here, what we can do, for example, we can draw us right here and say this is the present time. Let's just assume. So present time, we must be at some time right now. Good news, we actually know this value right here. We know that's about 13.7 billion years, so giga years. So we know it's about 13.7 billion years old. We know this distance. We don't really know the size because it's hard to measure. We don't really know what's going to happen later exactly. There's all these different ideas about the universe, but the shape of this curve, if you want to learn more about that, take a look at the HL videos about this. It gets really interesting because it turns out it's kind of mind-blowing what's happening. But say size of the universe, it's kind of like this. So we have another equation here. This redshift, the same one from before here that we had found. Sometimes, by the way, IB questions will be one where they kind of have you just relate both of them. This Z is equal to that Z, or Z if you're American, right? So that means that this quantity here, this R over R0 minus 1, can also be set to be equal to delta lambda over lambda 0, or it could be equal to V over C. So you can set them equal to each other as needed. So what is this going on? This is the redshift. That's just this unitless number. R is a scale factor. That's like the size of the universe. And we don't really put units. We're like, we don't know what to put here. Basically, it's the size of the universe now. And then R0 is like the size of the universe initially. What we're doing is we're comparing different things. We're saying, what size was the universe when this light reached us? Because in order for us to get a Z value, we actually have light that actually has to reach us. So when that light left, in order to get to us, there was a size of the universe when the light left. That's R0, where R means the size of the universe now. So this is a relation. So here's an example. We have a quasar. By the way, quasars are really distant light sources, some of the brightest things we know of in the universe. So quasars detected with a redshift of 3.2. What is redshift again? Do you remember what letter that is? That's Z. So you know that Z is 3.2. The question is, calculate the speed at which it's currently moving relative to the Earth. So find its speed. So we need an equation for Z. Do you remember some? Let's see here. If we go back, we have something for Z. We have this one right here. Z is just equal to V over C. It's actually that easy. See that? So we just have that. So let's go back here and say, fine then. So Z equals just V over C. That means 3.2 equals V over C. So if we want the speed, just get V by itself. Just put the C over. So that means you just have V equals 3.2 C. That is the answer. And I want you to think very carefully about this. Turns out that was that easy. The velocity that it is moving relative to the Earth is 3.2 times the speed of light. And you might think, no, nothing's allowed to go faster than the speed of light. Agreed. No information can travel the speed of light, like faster than the speed of light. What this tells you is that right now, currently, that quasar is going so fast, light from that quasar couldn't reach us. Because you see, the speed of light is the limit to how fast things can actually travel within the universe. That is true. That hasn't been broken. But there's nothing that says the universe itself can't expand faster than the speed of light. In fact, that's what's happening. This happens. So the universe itself is expanding faster than the speed of light, which means we have this area where we'll never be able to see information. We're never going to get new light from there. It can never reach us. It'll never get to us, which is a little bit crazy. Now you might say, estimate the ratio of the current size of the universe to its size when the quasar emitted these photons. What about the size of the universe? Then we need that other equation here, that one right here that has, where is it? R over R0 minus 1. So we'll write that down. So we'll say, fine, we have that Z equals r over r0 minus 1. It's actually this easy. We just put in the 3.2, which we got. So we have 3.2 equals r over r0 minus 1. We can just move the minus 1 over. That's a plus 1. So we get 4.2 equals r over r0. See that this is the current size of the universe. That's this size now compared to the size before. Size when the photons were emitted. So what it tells you, the universe is now 4.2 times bigger than it was when the light left those, when those photons left that quasar.